Okay, while we're on the subject of ionic compounds, we're going to go over the concept of what a solution is and also how to calculate concentration and deal with dilution. So a lot of chemical reactions, well, most of the ones that happen in your body and really most of the ones that you're going to see in our class and in a lot of chemistry classes take place in some sort of solution. It's rather difficult for solids to just react with one another. It's rather difficult for us to observe reactions happening between gases. And so for us, the easiest way to carry out a lot of reactions is for at least one of the reactions to be an aqueous solution. So first off, what's a solution? A solution is a homogeneous or uniform mixture of two or more substances. Solutions can be solids, liquids, or gases, and they consist of a solvent and one or more solutes. Classic examples that you're familiar with are when you dissolve sugar in water or salt in water, you've created a sugar or salt water solution where the sugar and salt are getting pulled apart by the water molecules and spread evenly throughout the liquid so that no matter where you were to take a sip of that solution, it would have the same saltiness or the same sweetness because the particles are spread out evenly all the way down to their molecular and atomic level. So there are lots of solutions out there. You can have solutions of solids, like when you make an alloy of metals, like brass, the atoms are spread evenly amongst each other. You can have solid liquid ones, which is one of the most common ways that we're going to see them, or that you're familiar with, like salt or sugar being dissolved in water. And anytime you have a solution where water is the solvent, we call it an aqueous solution. You can have liquid solutions like ethanol in water. Those are like alcoholic beverages. If you have gases dissolved in water, you can have a solution of that. The most common form of that would be like a carbonated drink where the CO2 is forced into the water at high pressure. And you can also have solutions where everything is a gas. And the atmosphere is a perfect example of a solution of many gases like nitrogen, oxygen, and argon, where you would consider nitrogen the solvent because that's the one that's present in the largest amounts, but they're all mixed evenly. So the solvent, think of it as the thing that does the dissolving, but technically it's just the substance present in the greatest amount. And the solute are the substances that are in smaller amounts, and they often change phase as they mix together into the solution. There's a very important expression, which is like dissolves like. It's a bit of an oversimplification, but it is helpful. The idea is that things that are polar tend to mix well with other things that are polar because their partial charges attract each other. Things that are nonpolar tend to mix well with other things that are nonpolar because of their lack of those partial charges. But things that are polar and nonpolar really don't normally mix. So the classic expression is that oil and water do not mix. There are lots of substances that don't mix with water because they are nonpolar. And so they'll form two distinct layers and they won't mix together. Whereas something like acetone, nail polish remover, is entirely miscible, mixable, soluble, all different terms with water because they're both polar, so they attract each other well and they mix well together. Although not included in that list, things that are ionic are sort of extremely polar. They are completely polarized to having positive and negative charges. And so things that are ionic are very commonly soluble in water. Not all ionic compounds are, but most are. And it's because the partial charges of water attract the full charges of the ions, and they're able to surround the ions and pull them out of the crystal lattice. An important note about this is that when you dissolve ionic compounds, you've now freed up their ions to move around in the solution. And so solutions of ionic compounds conduct electricity because of the free-moving ions. And so the term electrolyte can refer to these solutions that contain dissolved ions because they'll conduct electricity. But if you dissolve a covalent compound like acetone or like sugar into water, there are no free-moving ions, only dissolved molecules with no charge, and therefore those are non-electrolytes. So when talking about solutions, for us, it's going to be really important to be able to talk about them quantitatively. So we're going to talk about solutions concentration. Concentration refers to how much stuff, how much solute is dissolved in a given amount of solvent. Now, the general qualitative idea of something being rather dilute versus something being very concentrated is fairly intuitive. If you thought about food coloring, if you added 1 drop, 2 drops, 3 drops, 4 drops, 5 drops into the same volume of water, well, you'd be getting progressively darker and darker solutions, more and more concentrated. So those are relative terms. But for us, we want to actually be able to calculate how much stuff, how many particles, or how many grams are in a given amount of solution. So the way that we're going to define concentration, sometimes it's referred to as molarity. So you may hear me use that term, molarity. It's not the term that IB is going to use, but it's a term that you see often in America, and you'll see on the SAT should you choose to take it. But the molarity of a solution is the moles of solute, so the moles of salt or sugar, divided by the volume of the total volume of solution once you've mixed the water and the solute together. Now, the unit that they're using is dm cubed. That's the same as a liter. So if we put that into an equation, it tells us the concentration equals the moles of solute divided by the volume of the solution. If we rewrite it to give us moles by itself, N equals CV. The moles equals the concentration times the volume. So if you're tallying up different equations you have for moles, you've got N equals little m over big M for when you're dealing with grams. You've got PV equals nRT. And now you have this one when we're dealing with aqueous solution. There are a couple of other units of concentration the IB expects you to be aware of. One is grams per dm cubed, or just looking at the mass of something per liter. It's not very common to use it, but it's pretty simple. You don't have to do any, gram to mole calculation, just simply the grams divided by the volume of solution. And then one that's more important when we talk about things in very small concentrations is the unit ppm, or parts per million. It's the number of grams of solute per every million grams of solution. That sounds pretty complicated, but really all you have to do is take this grams per dm cubed unit of concentration and multiply it by 1,000, and you'll have the parts per million. So not something to overly stress about, but I just wanted to show you one example to show you what you'd get for these different concentrations. So let's say we took a 5.8 grams. I'll get rid of the underline here. Let's do some other calculations. So if you had 5.8 grams of sodium chloride, you would have 0.1 moles of sodium chloride. So if we were going to do the different units of concentration, well, to get concentration in molarity, we would do the moles divided by the volume. So let's say we put 5.8 grams, and just for simplicity, let's say in 1 dm cubed. Or if we want to make it a little more challenging, let's say in half a liter. So half a dm cubed is our volume. All right, well, 5.8 grams is the same as 0.1 moles. So 0.1 moles divided by our volume of 0.5 dm cubed. And so 0.1 divided by a half is the same as times 2. And so we would get our concentration is 0.2 moles per dm cubed. So that would be the unit in moles per dm cubed, or in the molarity. That's by far the most common unit that you're going to see. If you wanted that same concentration but in grams per dm cubed, well, we had 5.8 grams per half a dm cubed, per half a liter. So in a full liter, you'd have twice that much, right? It's times 2. So that would be 11.6 grams per dm cubed. So again, now it's just the mass divided by the volume gives us the unit of grams per dm cubed. And as a simplification, to get parts per million, simply take the value that is grams per dm cubed and times it by 1,000. So we'd end up moving the decimal place over 3 times, and we'd get 11,600 parts per million. So these are all referring to the same solution, but they just are different ways to express how much salt is dissolved in the water. 5.8 grams in half a liter is the same as 0.1 moles in half a liter, and therefore that's 0.2 moles in a full liter. That's how concentrated it is. 11.6 grams in a full liter, or 11,600 parts out of every million parts, out of every million grams, are sodium chloride grams. So those are some simple calculations there. We're going to talk about preparing a solution in class, and we'll do some of these practice calculations as well. But again, it's really just N equals CV stuff and then maybe some moles to mass stuff. The last concept to go over is dilution. Dilution is when you add more solvent, usually water, to lower something's concentration. It's a really useful technique to quickly create a lot of different solutions of different concentrations. So like when you do your own internal assessment, or if we do a lab in class and we want to create a lot of different concentrations, the best technique is usually to make one batch of the most concentrated version of your solution, and then to add water to it in a controlled way to make lower concentration versions of that solution. And so the idea with dilution is that if you take a small sample of your solution and add water to it, if all you're doing is adding water, then the moles stay the same when you dilute. Since you're not changing the amount of stuff that's in there, you're just changing how much water it is spread out in. And so if you think about it, the equation for concentration was N equals CV. So moles equals concentration times volume. So we can apply that equation and say that at the beginning, before we dilute, C1, the original concentration, times the original volume gives us the original moles. If we add a bunch of water to it, the moles still has to equal that same amount. So basically this equation says moles at the beginning equals moles at the end when we're diluting. And so this looks a lot like the P1V1 equals P2V2. It looks like an inverse relationship. And so that's how it's going to work. If you, when you add a bunch of water, whatever you do to the volume, so however much you increase the volume, that's how much you're decreasing the concentration. So the factor you increase total volume by is the factor you decrease concentration by. Okay. So as an example, if you start off with a 2 molar solution, and you have let's say 100 cm cubed of that, so 100 milliliters of that. Well, if you add another 100 cm cubed to it, so that its new volume is 200 cm cubed, so you just doubled its volume. So that means, what's the reverse or inverse of that? That means you must have just halved its concentration. So that means that it'll now be 1 mole per dm cubed solution, right? So you've just taken something, there were 2 moles in every liter, that's the concentration of it, and you had 100 cm cubed of it. By adding 100 more water, you've now spread it out to twice as much space, and so therefore it can only be half as concentrated as it was before. If you do a different example, if you take that first thing, let's say we add 900 to it, so instead we get 1,000 is our new volume. Well, you've just taken something and you've spread it out 10 times from 100 to 1,000. So by timesing the volume by 10, you have to now divide the concentration by 10. And so the new concentration of that solution would be 1/10 of what it was before. So you can use the equation here, but qualitatively, you could figure it out pretty well that it's an inverse relationship. And so whatever factor you increase the total volume by, not the amount of water you add, but how does the new volume compare to the old volume? That's the same amount that you'll decrease the concentration by. So again, in the second example, I added 900 water, but what I cared about was that the total volume is now 1,000, and 1,000 is 10 times bigger than 100. So since the solution has been spread out 10 times, the concentration of 2 will be divided 10 times to give me my new concentration. That's how dilution will work. We will do some practice using the equation and doing this in class. But those things about solution, knowing the terms solute and solvent, knowing that ionic compounds form solutions that conduct electricity while covalent compounds do not, knowing that to calculate concentration is N equals CV, and that there are some other units of concentration, but mostly you'll be doing moles divided by the liters. And that's, if you do a dilution, Whatever factor the volume increases by, that is the factor the concentration decreases by. C1V1 equals C2V2.